me great pleasure to introduce our next speaker, Graham Finch. He's a principal of RDH, and we abused him. Now that I have your attention, he came here as a graduate student to the first summer camp a long time ago, and we made him set up tables and chairs. So he then went from setting up tables and chairs to getting multiple degrees, tremendous experience, presented several years ago, and I think he's one of the most knowledgeable mass timber, building science of the younger generation around, and he's going to share with us his experience on combining different technologies in ways that many of us may not appreciate. So please give a warm Westward welcome to a graduate student who made it big, Graham Finch.
Thank you, Joe. It is always an honor to be here, and it's great to see everyone. It's after 2 years of doing online seminars, can't say enough for audience interaction and seeing a lot of my peers and colleagues here. So without further ado, I'm going to jump into a bit of a story here and some of the work that we've been doing and building off of the presentation I did in 2018. Not a lot has changed in some areas, but in this area where we're going towards today with facades that are actually built out of mass timber for high-rise buildings, there's been quite a bit of evolution, R&D. COVID was great to sort of push some of these along without the projects not necessarily starting up. So lots of neat stuff. At the same time, if you're not into mass timber, if mass timber isn't your thing, this is really a story about how you de-risk new and innovative facade systems. I can't tell you how many new systems I've seen in the prefabricated world in the last 5 years. And it is, there's a lot of buzzwords around prefabrication and, the next big thing. But there is a real need for more prefabricated facade systems of all types and all materials. And we see a lot. As an enclosure consultants, we have the luxury of seeing many projects in pieces. And, we're sort of collecting all that information, learning from the better ones and learning what not to do. So a lot of this is the process you would go through when you want to de-risk the riskiest thing you could do, okay? Or even the non-risky stuff. So in 2018, I talked a lot about mass timber and moisture. Kind of the same sort of story is still going on. We're doing some testing right now and building off of that. I was doing a webinar earlier this year, and and people were still largely locked up during COVID. And one of my colleagues' daughter, who was out of school, was actually sitting in the room with him, and she listened into my my presentation, and she's 5 years old, and she was, or 5 or 6 years old. And she was, taking notes during everyone's presentation in the seminar, and she summed it up perfectly. What do you do for mass timber? Get water off quickly. And if you want to know more about how to get out water quickly and protect it, we've actually written a few guides, and there's actually been 2 iterations since we talked last. You can go download those for free on our website. This walks you through a process, and I can talk more about it. I'll be around later on tonight. I actually have to leave at 2:30 or 3 in the morning to go catch a very early flight, so I'll be around. Maybe I'll stay up till then and we'll hang out at the clubhouse. So today I'm going to talk about high-rise facades, and this does apply to low-rises as well, but I'm going to use the high-rise as sort of the biggest and the tallest and the riskiest and the most pressure on these systems. And you look around any of our larger urban cities, there's a mix of materials, a mix of different systems. Nothing looks the same until a couple of years ago we started doing everything window wall, but largely a lot of variety in this type of system, right? And traditionally, this is a concrete, steel, and glass industry, right? That is the materials that we use for high-rises and we use for high-rise facade systems. And they can be site-built or they can be prefabricated. And it's important to realize, and we talk about prefabrication is not new. It's been around longer than me, precast concrete, curtain wall systems, steel systems, eave systems. So we're not reinventing the wheel here, we're building off of that. We're not inventing things new, we're building off of technologies and learning off what we did from before. So when you look at mass timber in this sector, when we talk about mass timber buildings, the primary use of mass timber is in the structure, right? So as a building enclosure engineer, what are we doing with the facades and the enclosure? Well, we're protecting that mass timber. But as buildings have evolved and as we've gone through more projects, we're starting to see mass timber being increasingly used in the exterior facades more than just the roof, and more innovation in the systems there. So there is some status quo being perturbed here with mass timber, and there's some justification for that as well. And at the same time, and we've had a lot of great presentations here about, carbon and, the challenges we're having with our industry, it's a great time to be pushing in this area because we have this really confluence of drivers that are pushing us towards, I'd say, a next generation or the next generation of, facade systems for all types of buildings and what these need to be. So when you look at the drivers for prefabrication in tall buildings, there are really three. And the first is physical, right? Height of the building, the accessibility of the sites. You look at any urban infill site left in most of our downtown cores, it's between other buildings. We can't get up all the sides, especially in New York. You got to get up the side of the building over top of an adjacent building. And so you can't, put a mast climber up, or you can't have scaffolding to install the facade piece by piece. So physicality and just the height and the accessibility is driving us towards prefabricated systems. Practical. We need to build faster for many reasons. Mass timber, we especially need to build faster to protect those buildings. Local labor availability, cost certainty, maybe not just cost, savings, but cost certainty. With this, there's a practical side. And then there's the environmental side, which is, driving this up. We need higher levels of airtightness and thermal performance, which, it's a lot easier to install, 8 inches of insulation on the ground than it is up in the air, and then put all the clips and the cladding attachments and everything else that goes with that. And so there's this desire to just do things on the ground, lift it up when it's already put in place. And then we're looking at low carbon. And, it's been really interesting going through project designs. The image on the left is the initial concept for a mass timber building in Toronto, fully glazed curtain wall system. The initial vision, very transparent. But when you actually run the energy models for where we need to be in Toronto for this building, it actually means you need walls first instead of windows. And so when you have, maximum glazing areas to hit these energy targets of, 40, 50%, when the majority becomes your wall, you start to rethink wall systems first rather than window systems first, and are more thoughtful in the design. And so we're seeing this shift where we actually need good, high R-value walls, not just spandrel panels and curtain wall, which maybe get you R5 or so, right? So we need true, R20, R30, whatever it is, out of that spandrel and that wall area with the correct glass. And so when you look at what is mass timber doing? Well, mass timber is actually being a bit of a catalyst for this. And the reason it's being a catalyst and why we're talking about this here with building science is that those types of buildings need those. They need the building, they need the facade to be fast. We're trying to do things from an environmental standpoint, and these may be constrained sites. And I shared this video last time in 2018, and this is a project we worked on 2006 or 2016, I should say. So it's old now, but it's been around, but it's still a great case study. And this is still currently Canada's tallest wood building. I'll share the US's tallest wood building here in a second, but you can see here the facade and the structure going together in lockstep to close this building in really within 2 months or so. And by the time they were getting to the upper floors, they were doing 2 floors a week once they hit their stride. And so you can close in a building and protect it from moisture and fire, construction fire protection, a necessary requirement in the IBC. And so this is why mass timber is that catalyst. And so the building, Broadcom, has used a steel frame prefabricated facade, and I talked about it a bit last time and where we were in the evolution there. We've gone on beyond that. And And you can see that, that was quite a successful implementation. And there's nothing wrong with you using a steel frame prefabricated facade on a mass timber building. You could even use a precast concrete building, or precast concrete on this building, or you could use curtain wall, whatever you want. It's just going towards a system. And you'll notice that these are larger format panels that have windows, pre-installed, right? If you look at the Ascent in Milwaukee, which is the world's tallest wood building, I don't know if you know it, this is, home here in the US. This is 284 feet. Just, finishing off, this is window wall on a mass timber building. So it is, it uses a smaller format prefabricated system, but it essentially is, a glazed, system that's being put over top. So the only math, I don't think I have any charts in this presentation, so, but the only math, and sort of take away why we're going here, you look at a high-rise building, wherever you are, you're gonna end up with a site-built or prefabricated facade. Pick one, right? You gotta do on site, you prefab it. And this is market, design, and speed dependent. What we've already seen in the last, I'd say 5-10 years, is when we have a higher energy efficiency goal or passive house, and especially in our market on the West Coast, we're starting to see a shift towards prefabrication because of the amount of insulation and the thermal performance that we need. And we're also shifting away from fully glazed curtain wall and window wall systems because we can't get there to the performance we need to with the systems that we're currently on the market. I would say that there are projects now we're getting curtain wall systems up to those levels, but it takes some innovation in that area. When you have a mass timber structure and passive house and it's tall, prefabricated facades are the way to go for sure. It's going to make your life the simplest and take that variable out of the equation. When we have a low carbon goal, and this is what's been asking for this, when we have a low carbon goal, now it's like, hey, well, I need a prefabricated facade, and maybe I should do it out of wood. Maybe I can do it out of a lower carbon material than aluminum and steel and concrete. And so the reason that we're seeing this is there is this demand that's sort of been building up where, hey, we need all these things in these buildings now. And I used to call it like the trifecta, passive house, mass timber, prefab. And a lot of projects are going towards this approach, at least if you're working on some of these mass timber buildings. So how do we get there? How do we build the industry for this? And as I'll remind you, we're a consulting firm. We are not a manufacturer. We've worked with many manufacturers to help them, but we are doing engineering, and we're seeing lots of stuff. We're pulling in lots of things here and sharing and pushing things forward the best we can here, and working with many talented teams on this. So if you look at why, there's the obvious aesthetic arguments, to any of the, architects in the room and others that appreciate, wood as a building material. These look really nice. You can do a lot of different things, but, the exposed wood is, especially in office buildings, we're seeing that really, a desirable, attribute of those buildings. So there's definitely the aesthetic argument, could be a preference, but essentially there are enough people that want this and are asking for this that we're seeing the argument to do this. There's also the carbon argument, right? And we've had a lot of discussion about carbon. I think everyone appreciates that there's, operating carbon and then there's embodied carbon. And the, operating carbon we're addressing with energy efficiency and our grid and all the great things that we've talked about in the last couple of days. And embodied carbon is looking at the materials you're using for that building, and in the case here, the facade. And so we're trying to reduce the amount of carbon in our facade systems. Again, it's a portion of the building, but reducing the carbon in the facade systems by using materials that have lower carbon intensities or materials that actually store carbon, and things like wood would be and other biogenic materials would fall into that. And so the trend, and the reason this is happening, I'd say, on the West Coast and British Columbia and other places early, so we get to be the bleeding edge of a lot of this, is we have a low carbon grid in BC in particular, it's all shared, but there's definitely a driver there where we look at carbon, and the operating carbon actually becomes pretty small in a passive house building. The embodied carbon actually becomes the bigger piece of the pie. And so when you're looking at a pie and you see the operating or the embodied carbon bigger than your operating carbon, that's when you start to think, hey, maybe I could do something about that piece of the pie. And so that's why we're looking at this. And so we're engineers. We had to look at the numbers, and I actually didn't look at this for a while. Then we have a PhD student at Penn State working with us, Samantha Leonard, and a very smart woman. And she's doing her PhD in mass timber in carbon in mass timber, and looking at a whole bunch of optimization of that. And we were talking a couple months ago. I said, I'd really like to dig into the real numbers of carbon in these mass timber facade systems, and compare them to some other systems that we're looking at for projects. So we dug into this. So what we got here is we got the embodied carbon comparison, primarily looking at the structure, but it's a large format panel, so imagine something 20 feet by 10 feet. We're looking at A1 to A4, so just the initial, plus transportation to site. We use Chicago as a city here. For essentially everything's coming sort of from regional area there, though. And we've got mass timber, steel frame, aluminum frame. The aluminum frame uses an insulated metal panel to give it strength, and then precast concrete. And we've been looking at this, and you see a lot of carbon numbers, like how do you make sense of this? So actually the interesting thing is when you look at pounds per CO2 equivalent per square foot of facade, those numbers actually, they're not zeros, they're not a bunch of decimals. And it's weird, it's totally coincidental. Those numbers are very similar to the weight in the pounds per square foot of what these walls actually were. So you don't want to confuse the two, but some of these walls are 20 pounds to a square foot, right? But so when you look at mass timber, and looking at mass timber first, I'll show you in a second here with storage, without carbon storage, CLT or LVL, which represents mass plywood panel and some other products that are veneers rather than lumber, you're at 16 to 19. So you're lower, but steel stud framed, cold form steel is actually pretty efficient. Lightweight, it's energy, it's engineering optimized. This includes, by the way, all the components for structure, the attachments, the screws, the insulation, the membrane. The aluminum is higher, and you can see aluminum is higher. Aluminum has a higher embodied carbon in the production. That number is coming down with recycling and getting better data on that. The aluminum looks a bit higher there because we also used insulated metal panel. That's just what the system was using. So that insulation part in the dark blue is a bit higher than you see the other ones that used a mineral wool or an EPS there. And the precast concrete. And the precast concrete, of course, structure, concrete's a bit higher, but concrete is not terribly worse than these other systems. And I think that's important to realize. If you look at the structure, concrete's twice, or maybe 3 times as much as say CLT. But when you put it all together, it's 16 versus 28. That's double, right? That seems like a lot. But the cool thing is when you start looking at sequestering carbon or storage, and if you actually can get your storage and the end of life doesn't, allow that wood to rot away, we can actually get to facade systems with the storage. And if we look at the storage and understand how we're going to, address these buildings long term and not, dispose of that wood and let it rot away in landfills later on. And the other thing too is for now we're trying to figure out how to flatten the curve, right? And so wood can help us in the short term until we solve the crisis. And I think what you see here is you go 16 down to 1 and minus 1, pretty much 0. And so not intentionally, but coincidentally, the mass timber, these facade systems, actually can truly be 0 carbon. Okay, net zero, and it's net zero because the wood offsets whatever else you're putting into it. And so the story there is that you might use this because you truly want a low carbon facade system. And when we look at the mass timber projects to date, the structure savings isn't quite enough to offset everything else you put in it yet. But at least on the facade, we can start making some inroads there, and that's why there's a desire to do this. So there is some reality to getting pretty close to 0. Now, when you talk about wood facades and tall buildings, the first thing usually comes to mind is fire. And so how do we make sure that these buildings and these facades are fire safe? And there's two ways. And, if you talk to any fire engineer that's doing a lot of this, you either encapsulate it, so you protect the wood, or you design it so that it'll actually char. And the idea with char depth is that the mass timber in particular will burn at a predictable rate, and you can essentially design your structure to be the protected part, and the sacrificial layer, which means you use more wood, ends up being that fire protection. And so when you look at facade systems, we can either encapsulate or do the char method. Now, if we go to the char method, we need about, 2 more plies of, 2.5, 3 inches, a bit more wood, depending on whatever the fire rating is. Generally, it's like 1 millimeter per minute of char, and there's a bunch of, numbers around there that are the structural engineers and fire engineers will use, but you can use char as a way of doing this. When you look at not just, the char rate, but when you look at the facade systems, you need a fire resistance, right? And the fire resistance can be achieved by encapsulation or the wood itself. 4 inches of mass timber will give you an hour, of fire resistance. But that's not as important as, the other aspects of this, like exterior fire spread. So NFPA 285, and then fire stopping performance. If you've got a 2 or 3 hour floor, then you need to have a 2 or 3 hour rating at that interface. And you know what? Well, at the very end of this, I'll show you the results. We've tested this. So what do we do for fire protection? We either, thin mass timber encapsulated, or depending on what the structure is doing there, or we have char. Generally, and the kicker here, and where you're going to see some of the changes, when you have a non-load bearing exterior wall, it generally is a 1 hour rating, unless you're really close to another site. But you need 2 hours for load bearing wall, right? So 2 hours out of 4 inches, you won't get that, so you need to encapsulate it. But if you only need a 1 hour rating and you're non-load bearing, which if anyone's designed high-rise buildings, exterior walls are rarely non-load bearing. They're almost always, non-load bearing, infill walls or hung walls. The load is taken in by cores and columns and shear walls inside the building, not on the exterior. And so this is where the opportunity is, okay, we're going to hang lighter weight wood panels that'll hang off, they'll be non-load bearing, therefore we only need 1 hour rating. When we look at facade and building movement considerations, most people think about, okay, I can do mass timber, I'm just going to stack it up in a platform frame. And we see this with low-rise construction, but when you put, shrinkable wood in your load path of especially a taller building, that matters. And so you don't want to put shrinkable wood, like in the CLT floor slab, in your load-bearing walls. So you might balloon frame it, like the application in the middle there. Or when we're talking about non-load bearing, we'll either hang it, or it'll be infill with some sort of, steel stud track or something to, allow it to move, or allow the structure to move and not put load into the structure or into the facade. And this understanding of how facades work, and you have to decouple structure from facade, is one of the biggest challenges we run into early on a lot of these projects. Like, we're gonna use mass timber, but that wood, we don't want it to be load bearing. And there's many good reasons not to make it load bearing, and that's been one of the challenges we've run into, is how do you make this non-load bearing, hang it safely? How do you deal with the structure moving in an earthquake with that, so it's not taking load or falling on, getting knocked off the building? And that's the fun of facade engineering, especially in earthquake zones. Make stuff stay on the building in a big earthquake. And so when you look at non-load bearing facades, like, you can hang them, like there's a curtain wall, right? You hang it from the top, generally a dead load anchor, and then you have your lateral load being taken by, say, a stack joint, lateral or stack. So it's everything's hung from the top, and the movement is taken in the stack joint. That's pretty typical way of facades. And now you could move this to the inside. It could be, on the inside. You could now support the panel at the bottom, either on the outside of the slab, or this could be sitting on the slab itself. The top of the panel needs to be braced there because it's just, sitting there, right? And that's where you have, stack joint or a top restraint, like a nested track, steel stud track, right? Holding it in. So you either hang it or you bottom bear it, and then you take about movement somewhere, and that movement that's the tricky part. That's actually the hardest part, because you have to take movement in wind, building movement, earthquakes, whatever's going thermal, and not leak, not, water get in and not get loaded or, get loaded to fall off the building. So the key technical criteria for facade, sort of, broken down simply, if what do you need to do? Don't break and don't fall off, right? And it's, easier said than done sometimes, but you have imposed structural loads from wind, seismic, building movement, thermal movement, possibly blast and impact resistance, depending on what you're designing. Don't leak, right? And don't leak to wind-driven rain, and also air leakage. Now, nothing's going to be perfectly airtight, just we need to get that air leakage rate down as close to zero as possible. That's the goal there. Don't leak, get the air leakage as low as possible, that it's not a contributing factor to the overall air tightness. Don't sweat. Condensation resistance, thermal performance. Don't burn, right? Fire performance, combustibility. Look good. I put that at the bottom, but it really is probably the reason you would start doing this. And also sound good. Acoustics are quite important. Okay, so the acoustics of these systems, we were talking the other day with a gentleman, we were mentioning how acoustics, Joe, we need an acoustic session next time. We need more people talking about sound. And how do you do this? You can engineer a lot of this, but you actually can't solve all the problems with engineering. And so you need to do physical testing, and you need experience. And so it helps to test things, and I'm going to talk today about how we test the risk out of systems. And so we avoid this. Now, I've tried to find a picture of a building with things falling off, and usually people aren't at the right place at the right time. But why do we do testing? Why do we do all these things? That's just like that's what we're obviously trying to avoid. But there's also subtle things. This is a project I worked on about 10 years ago. We're doing air leakage commissioning, unfortunately, at the end, and we're like, it's pretty leaky, so we put some smoke in, and there's a guy inside putting smoke into a drop ceiling, and this thing is leaking everywhere. And why is it leaking everywhere? Well, no one did any early testing. You should have tested part of this system and details before you did the whole building, right? And yeah, call the fire department. This is one of my favorites because it... Oh dear, we've crashed. It's coming back though, look at that. Should have been a Mac. This is me in my younger years, walking around a job, and a very rotten column that I probably shouldn't have touched. And above me, the balcony starts to collapse. And the glass in the guardrail starts to take the load. And fortunately, we had a contractor with us that fixed that before it was... And the other reason we test, you don't know if you notice this very carefully here, but optical aberrations and other issues. So the reason you get materials, this is curved glass on a project, so there's some issues with the cladding, but the glass is a huge problem on this. And so the reason you do mock-ups and testing is you can see, and you actually go to these things even during COVID, to make sure that you're not going to run into weird stuff. So how do you de-risk new systems? So, you got an idea. The idea can be built whatever, as big as you want, little as you want. You have an idea. The first thing you usually do is design, engineering, some prototyping. 3D print stuff, right? 3D print, build little mock-ups, do little benchtop tests. Then you start getting into smaller scale, maybe 2 foot by 2 foot or 4 foot by 4 foot, and you do detail iterations. And I've gone through this a number of times with different manufacturers recently. And it works quite well to work out the kinks. Is that gasket really fit? Is it going to leak? How do we connect the things together when it comes together at a 4-way joint? And then after that, you do a full-scale performance mock-up, something at a lab or that is reviewed, and you get a test report. And then you make tweaks. You're rarely done. You'll learn something in that performance mock-up. You make some tweaks. And then you're ready for small projects. And you're ready for, real-world iteration. iterations of your system, right? So don't go for the big, don't go for the moon right away, but go for, you know, little things. And this process can work quite well. It's hard to skip some steps. Some people want to jump right to buildings from their prototypes, and this is where we usually get involved, because it's really risky to go right from, hey, an idea, never built it before, never even tested it, to a building. And this is why we have performance mock-ups. And so a PMU, or performance mock-up, is, you know, essentially a larger scale test. We usually include a corner, 2 stories, as big as it, you know, can be for the test lab. So usually something like 10 foot in the short wall by, you know, 20 or 30 feet on the long wall, include corner details, windows, balconies if you can. And the idea with the performance mock is you're going to test it for temperature differences, rain, precipitation, wind pressures, your air pressure, and the movement of the structure. And the reason we usually do these at test labs is we need to move the structure behind these facade systems. And that's kind of hard. You can do it with forklifts and stuff like that on you know, off-site, but you know, the labs are better set up to often, you know, do that in a controlled manner, and then they have all the test equipment. So when you look at the structure for these systems, and this is a one we've been using recently, the structure, the floor of the structure is designed so it can move up and down, side to side, and in and out, so you can simulate building movement and seismic movement, and even potentially, you know, wind in that case. But it's designed to allow and control the movement, so you can impose the load onto the facade and make sure that it doesn't break when you slide it around. And so when you look at a test chamber, you build your facade around the outside, they put a roof on it, there's a floor, and the lower test floor is usually where you're undergoing that movement, so you got that interface at the sill, and then you got the upper floor in there. Now you can make these bigger, you can make them smaller, but the general idea is to test as much as possible, including, you know, movement as you go through the process. So a typical procedure is you do a lot, you know, you do it, I'm going to go through these in a second here, but you do air leakage testing, you do water testing in a couple different ways, you do some structural wind load, then you repeat your air and water. So you're repeating air and water testing every, you know, 3 or 4 times here, so that you actually, you know, understand, is it still air and watertight after, you know, we've moved it around? Is it still air and watertight after so much cycling? Is it still air and watertight even at the end of a, you know, monstrous earthquake? Yeah, that'd be good to know. You know, if we ever have a big earthquake on the West Coast, like the amount of, you know, talk about repairs there, but like, it's going to take years, you know, if not decades, to fix those buildings. Look, you look at New Zealand as an example, and so can we make these buildings livable post-earthquake? You know, not to mention services and stuff, but, you know, can we make these, you know, livable post that? So there's some desire to do that for resilience. So air leakage, you know, there are ISTM standards for all these things, but essentially you're measuring the infiltration rate, how leaky is your facade system, and you get a large enough area here, you can get a pretty representative number and understand, you know, is it gonna, you know, work for, say, your passive house project. And, you know, what does it look like? Yeah, it's pretty boring. You're just measuring a number. They pressurize, depressurize. They put some plastic on the outside when they're doing the pressurization test there to measure the air leakage rate very carefully with, you know, laminar flow elements and flow tubes and stuff like that to measure the air leakage through your facade system, okay? And you do that many times, so after it's moved around, you're gonna get a number there. The funnest part with air leakage is actually the diagnostics, though. Usually, the first time round, you put it together, yeah, it leaks. Doors, I don't know, doors just love to leak, I don't know. These are doors we put into a system. They look great, but, you know, weren't installed properly or not adjusted properly. So you get the manufacturer there, they fix their door, and then you go on. If it's really bad, you end up blanking it off, and you say, okay, that's excluded from the air leakage of this test, and, you know, maybe we'll find another door, hopefully, that'll work. But these are the things you learn, right? It's good to learn now, not on the building, when you have 500 of these things. The next test is a static pressure water penetration test. This is, you know, it's basically suck on the inside of this and try to pull in water that's on a calibrated water rack. A lot of us do this in the field, 1105 type testing. And essentially you're just trying to pull it in, and the pressure you test to depends on the application. Now in a high rise, if you're designing a new system, you usually test to the maximum. So 720 pascals, you know, 15 PSF there. Dynamic water penetration is much more interesting, I'd say, to watch anyways, because you got a big cool aircraft propeller spinning around and blowing water at it. And this again is just a different type of water test where it's dynamic. You're blowing water at the window with, and you're measuring pressure that's induced by this fan. And it's easier, if you look at a video of this and you can see what's happening here. You're essentially, you have a spray rack, and then you can see the amount of water going off there, right? That's an incredible amount of water. And on the inside, it's even more fun. This is what you're seeing, right? You're seeing a lot of water. It's like, maybe you've been in your house when it looks like that? No. But this is the extreme case, right? So if you can pass this extreme case, maximum, water spray here, then you're going to be in pretty good shape. Now you could test to lower pressures and so forth, but if you're trying to de-risk and look at, worst case after many years of performance, test to the max. Structural wind loading, this is where you then apply with fans a load, a suction, a positive and negative pressure to see how the facade, behaves under those conditions. So and so you essentially suck and blow very high pressures to your design wind speed pressure. So, thousands of pascals here, right? And this is not a good example of, this is what you want to avoid, but this is under pressure here. You're going to see something moving here in a second. Apply the pressure. That'd be bad. Good thing you find that out now before it's hidden, right? Yeah, so you learn so much from these things where you're like, oh, well, maybe we should put some shims in there or design that differently. Well, you got some tolerance you got to address some other way, right? Interstory displacement, this is one of the funnest ones. So, 501.7, or AMA, not AMA. This is a vertical displacement. So this is up and down. And then we get interstory drift, which is side to side. So up and down, you can see a window wall system here. You can see it's just subtle. You're only testing, ½ inch to an inch. This is how much your live load deflection or long-term movement of your floors might be relative to the facade. And obviously, that's why you have joints every floor, or maybe 2 floors in some systems, where you're taking that movement, so you're not loading that facade. Now, this would fail if we loaded this, let's say, and then the glass would start to maybe break, or the doors wouldn't work underneath because they've started to see some load. Now, my favorite one is the lateral interstory displacement. This is the earthquake test, or representing a case, maybe high wind in a tall building, where the structure is going to sway. In our tall buildings, the structure is going to sway. That swaying, we don't want that smash in the glass, and we don't want to smash in the corners. So how do we address this? So we do elastic, and then we do inelastic. So elastic is your design loads, and inelastic is your extreme, your proof loads, the mega event, let's say. But your elastic event, this is where it needs to move around and come back and still remain air and watertight, and not have any ill effects of sliding around there, right? So you tend to repeat this in a bunch there. You can see this is how you can see how a window wall sort of flexes, right? It takes the movement into the corner, but those you can see it sliding in and out of the corner pieces. And so, yeah, we can do structural glass at corners, but then you got to take this movement somewhere, right? You can either take it next to the corner, or you can take it in the corner, but this is what limits a lot of our facade design, especially in the seismic regions. It's just like there's too much movement, and so we need to be able to accommodate that. And then we've got thermal cycling and condensation resistance. This is where you take your facade and you build a chamber around it. And lately with dry ice, which is super dangerous, but because it's oxygen depleted environment, it's full of nitrogen, but you fill up the outside. So you hope your facade's not super leaky here. And this has happened, and and sadly in places where we had PMUs overseas, people have died from this. And so you got to be super careful. And if you're going to go review those things, being super careful that you're not in an oxygen depleted environment. We used to do this a lot with heat pumps and things like that, freezer coils. But a lot of labs now just use liquid nitrogen. So be careful. But you basically wrap your facade with an insulated box. This is on the inside of one that 15 years ago I looked at, and they wanted to put window wall system they were developing in Vancouver in Edmonton. And They also didn't want to change the heating system. And so there I am outside here, poking around. So this is cooled with, you can see the coil there. It says not liquid nitrogen, so I'm safe in there. But you're taking measurements. But you can see there's a whole lot of frost. The doors actually froze shut in the mock-ups. They're like, okay, maybe you should add some electric baseboards. So not only is it a mock-up for your design of your facade, but also for the building, the mechanical system. And so we learned on this project that, yeah, the only way to make this work, electric baseboards below that door, you gotta blow more air continuously. Like so yeah, you can fix a facade that maybe shouldn't be used there with mechanical, but that's not the best way, right? And so you learn these things. And now, in higher performance systems, you don't want to see any of this, of course, but this is, how you de-risk and you understand the whole building system interaction. Then after you've done that, you do a structural proof wind loading. This is really fun too. So this is where you get to blow up your building, your facade like a balloon. And put the maximum, 150 designs, you're stripping away, in many cases, your factors of safety at 150%. You might have a bit more capacity in there, of course, or you should, but you're going up to 150%. And this is the side view, you'll see sort of it moving. This is, thousands of, pascals. But you can see it more in here. Glass is a good tell, right? And you can see the glass going, noop, 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 right? So you can see it. They can see the whole facade system there moving back and forth though too, right? This is what happens in high-rises on a wind event. This is actually happening in, 50 stories up. You don't see it. Sometimes you do, which is scary. Now, the last one you do is inelastic lateral interstory drift. And this is when you push it to that extreme event, the big earthquake, or just whatever design. You want to push it as far as it can go and see how much it can move. Now, things can leak after this. They may or may not, but things can't break and fall off. If that corner piece or piece of glass breaks, this fails. So you are de-risking for an event that has a low probability of occurring, but anyone on the street will thank you, when that does happen. And you should be able to live in that building afterwards too. This is a large format panel. This is a drifting panel. So this panel doesn't flex, it actually drifts into the corner. And the magic there is how you make that corner cladding not fall off and how you have your joints go together. And that's like this one too. It's like, this is how buildings move. It's fascinating to watch these. I love these because you get to see what's really happening. Because it's not just a static thing anymore. It's actually living, right? No, but they don't need to breathe. Fire testing. You may, or you're going to build another mock-up for this, but the fire testing mock-up, NFPA 285, S134 in Canada, and 2307 are typical fire tests. You would do on a facade system. They look slightly different, but you're burning, through a window and onto the underside of the facade. And these are the fire tests that you'd want to do, or you should do, or have to do because of the code requirements. And then there's some additional security and safety testing. Now, in Canada, we rarely do these things because we don't have people blowing up buildings, fortunately. But, there are, and we don't have hurricanes. But more and more, we are starting to test systems that will have some security or impact resistance. Just did a project where we had, it was a jail. And jails now get windows, not bars. And they get nice big windows. And they have to be bashed for 2,000 blows. And it's an amazing test, and you can do that as part of your mock-up or separate, but 2,000 blows on a wall and then the window, and it doesn't, you can't get a hole, that you could fit through. That's pretty cool testing too. Don't want to be the guy doing that, 2,000 times, but. Now, how are we pushing wood facades here? So what are the developments in the evolution to date in this sector here? So I presented this. I talked about Brock Commons or UBC Tallwood 4 years ago, and it was new at the time. And this was the first steps. And I'm going to quickly go through this and get into what we've been covering since. But for those who weren't there, this is really that first step towards going to prefabrication for mass timber. And this was on Canada's tallest wood building. Part of that project, we had the benefit and luck, and I think part of the what made this successful is we had a competition early on before the design was finished to have companies come to us and say, okay, here, give me your prefabricated facade system. So we had a wood system, we had a steel frame, and we had concrete. And all of these were, built or designed, prototype, and they were judged, and they had a scoring, and the cost of these were all they were close. The wood was a bit more than the steel, and the precast was sort of in between. But they all were pretty close to the project budget. Ultimately, the steel frame system and the manufacturer that had the capacity to take on such a project, and so we went forward with a steel frame prefabricated wall on this building. And it, essentially cold form steel, HSS and other connectors, gypsum, exterior insulation, cladding, windows, everything pre-installed, in the factory. At the same time, we were kicking around this idea of how you do this on a mass timber, and you could basically swap mass timber in for the steel pretty easily. The challenge is we couldn't find someone to build this, and structurally and everything else it worked, but we couldn't find anyone to build this. And so the challenge at the time was, industry capacity or interest to take on this risk. So we said, okay, we'll park this and we'll keep working on it on the side. And so, of course, we did a PMU of that steel one. You guys have seen this. And we learned a lot from that PMU, like, corner panels probably shouldn't be fixed. They need to float a bit. Otherwise, they would have broken off. But we also tested the joint system and the windows. And so a lot of iterations and tweaks were made because of the test. And it went quite well. The project, it was de-risked, and the project went, quite successfully. A lot of people ask, well, how did you connect these panels together? And we took a pretty simple approach, and we tested it out. We needed a seal we could do on the inside. We couldn't go on the outside of the building. We needed something on the inside. So we actually brought a sealant joint, just from the WRB and air barrier on the exterior, behind the exterior insulation, into the joints. And we designed, and we had the panel joints configured such that we could access that from the inside. There's no real magic there. It's a low modulus structural silicone in a buried mid wall. And the key with this was it's outside of your structure, which is important. If you try to do this inside of your structure and you got structural penetrations coming through, it would be a nightmare. So we did all the sealing in the in the wet area there, and of course it was tested. And the elastic movement here was not too large, but essentially the testing was sort of looking at it. It looks really messy, right? That looks like awful, but they're still the right 2-to-1 profile. Not the great tooling there, but this is what happens in mock-ups. So that went forwards. You can see the panels coming in. The male, it's just simple male post, female receiver that's slotted. You can see here, you can see the slotting connection. So that panel can drift side to side, but it's not going to go out. So this is a very simple way of doing this. And you can see that sealant joint. There's the backer rod going in, and the sealant joint is outside of that. So you could get the seal continuously behind. And so this just became an exercise of QA/QC on that sealant joint that had been tested out. And it was well within the sealant's capacity to take the shear and the movement. Even at the extreme cases, it would potentially perform. And where did we have problems during construction? Well, where installers maybe didn't go all the way behind, but that's easily, someone walked along and inspected all of this. So the other thing we found too is we did testing of this, and we found that even where it wasn't perfect, it leaked air, but it didn't leak water. So at least you de-risked the water coming in, but then we used air leakage testing to find those leaks and patch them up. So, the system worked, and the insulation and the vapor barrier in this case went in, and you always do field commissioning to follow up with something new. Doing something new and not testing in the field, just relying on the lab test. So the field commissioning found a few of those, workmanship defects. And so after this, we're like, okay, this works. That sealant joint really could be better, do something different there, right? Evolve to something else. So we had the opportunity pre-COVID and into COVID to work on Katerra's only mass timber project. Katerra's no longer, but a lot of great lessons from this project, and I'm here to share those because Katerra's no longer around to do that. And this project, it was going for passive house, net zero, even with the solar array, and so they had a really stringent performance requirement. Working with Michael Green, architecture, on this project, I don't know, we early on were like, oh, let's do what we wanted to do prefab, and Katerra wanted to do this too. And for some reason, we all decided that we should do 2-story tall panels. panels. And then one of the reasons we did 2-story tall panels in this job instead of the nice horizontal one is our commercial space in our university, so we've got 15-foot floor to floor, and so we couldn't do a 15-foot panel because it was too tall. And so we said, okay, we'll do 10 foot on its side, and we can put it on the truck, which changed the limitations, but it's still the same sort of concept in the end here. So the challenge with 2-story tall 15-foot panels in a seismic zone is your interstory drift is like, the elastic is like 1.5 inches, and inelastic is like 6 inches. So we need to take 6 inches of drift, potentially, between these panels with terracotta on the outside of this building. Back to the drawing board there, how it's super flexible. We'll get into that. So we actually, this is where we introduced the notion of like a sliding sort of, this was a steel chicken head type connection. We initially wanted to put, aluminum curtain wall chicken head in the wood, and because that would work great. You can easily slide 6 inches, and then you just got to dress your corner panels. So we had this structural connection, and then we had to come up with a flexible connection at the joints. Interesting thing about this project, and you'll see in the pictures in a minute, we initially designed this with mineral wool on the outside and clips, and because of the movement and the panel joints, especially at the corners, we ended up with this crazy structural lattice, and where this project was being building, they couldn't find someone that wanted to do it. And so, the great idea, but would have worked in Seattle, but they couldn't find anyone, the contractor, to build this exterior insulation system. And so, what happened is we ended up going to an insulated metal panel. And so they could find someone that wanted to put an insulated metal panel on the outside and then attach everything through the insulated metal panel. So it became more complicated than initially was, but the concepts for the facade and the joints carried through. So you got a mass timber structure here, beautiful during construction, nice exposed, long spans, great for an office. The facade system, because we're going in flat and we're flat packing this, so we're not putting terracotta on in the factory. We're not putting windows in the factory because they're too large to be put down horizontally. So we prepped everything for the windows so the windows could be quickly installed. So we got air and water resistant barrier membrane, the exterior insulation with insulated metal panel in this case, all of the insulations on the outside. So we don't like, the risk we thought of it here too initially is like, what if water gets behind the metal panel, right? And that's, so we also added a water control layer. Essentially we caulked up the face of the insulated metal panel with a sealant rather than just relying on the insulated metal panel itself, just from experience with them. Not the ideal world, but in Spokane, very dry climate, very low risk, so tolerable risk for something like this. And then they pack it up, put it on the truck. This is the concept for the structural connection there, just a steel connection. It's into the wood. Don't love steel against wood over time, but you could get a metal to metal connection that's sort of embedded in there, and that was sort of the initial concept, but that's the idea there. And then we had very flexible air and water seals, so silicone strips that are attached to silicone that can design and take that movement so the joint's wide enough to do that. So a bit complicated, right? But we'll go forward. So on site, the panels get hung from the middle, and then they got wind anchors on top and bottom, plus the chicken head there on the top, I should say. And then the windows going on site. And then we got a lot of joints. The odd joints we got to seal up, right? Yeah, so joints. And the problem with the joints, COVID and everything else, this got sort of shifted into winter. It really sucks. It's 0 degrees Fahrenheit putting joints on. But they did a pretty good job. I would say that they did an excellent job for the conditions. The challenge, and then you can see that actually, you can see the type of joints here. And on the inside, the silicone spray from the fire floor to floor actually goes into that joint there as well. And so, what is a very flexible seal? This is like pre-project where we're trying to figure out, is this going to work? What do the joint profiles need? What do we do? Is this going to zipper if it's wrecked? And so, but you can, this is the bench test before the actual project, right? And so you can see some of the challenges you'd have in that. Now these are, extreme events. In this case, we're pushing it this far, but we still need to make this work within that elastic range that the building could sway and not have the facade tear, right? So the structural brackets, 2-story, they're hung panels, gravity in the mid, and the wind top and the wind bottom into the chicken head connection there. Now, the PMU. Now, this project was supposed to have a PMU. It got delayed, and the construction had to start, so we had to shift the PMU from a lab to site after the building's built. Now, what could go wrong, right? Now, what could go wrong, but if what could go wrong, could it be de-risked on site? And that was part of, okay, if it's not gonna work, can we fix it on site? Yes, we can. In this particular, the way we designed this, you could fix it. So the PMU included all the joints, the window installation, and built a chamber that we could do depressurization and everything else. We'd done enough small scale movement testing that we were comfortable with how that goes together. The air leakage testing, put on the smoke, we found a lot of leaks. There was a lot of leaks, the QA/QC, the pick points weren't sealed like properly. There's, you can't just shove spray foam in a hole and expect it's gonna be tight, right? Like there was supposed to be some peel and stick and other things. And there were some workmanship issues. Fortunately this is early on before they finished the rest of the building, so you at least figure out what the process is to seal this up. And there was a fair amount of water penetration through defects in the silicone strips in the installation there. So what do? Well, you have to inspect all the seals, repair and verify fixes. Could you have avoided this? Yes, you could have avoided this with better QA/QC. Maybe the schedule wouldn't be so bad where it was. But fortunately, it was a fairly accessible and easily. They were able to inspect all the seals. We came up with this. You can see the guy with the pressure gauge there, and we use smoke. And as they pressurize this, and they're sitting on the outside, they can see where the leakage is coming through, and they can seal it up right away. And so we had a system of thumbs. Good, bad, middle, lot. And my colleague Luke's hand here, and Luke's in Boston actually, he's not here today, but he came up with quite the hand system. Has some famous hands now. So 100% QA/QC works, but in the evolution of development here, we need to do better. Silicone strips can work, and there's still application for them, but 100% site installed seal for something that critical, we can do better, right? Now, the good thing, we actually, we did a full building air tightness test. This is one of the tightest buildings we've ever tested. It is the tightest building at the time we tested it. This building, you can see the red dot compared to all the other buildings that we've tested in Washington State and BC. Was very tight. So in the end, it worked. In the end, it was a success. It cost a bit more to get there, and we could do better. And so we said, okay, how do we do that? So you can see it wrapping up. The exterior insulation over the insulated metal panel, don't get me started. That's a beer story. But terracotta, beautiful looking building. They've had some issues with the terracotta. They've installation errors they've had to fix, but in the end, a successful project and looks quite nice. It is, hitting its energy and targets there. On the side of this project, we're also working on a project in Vancouver. Great for learning. Project's never going to get built now, unfortunately, but maybe fortunately. It depends how you look at it. So on this particular project, they wanted wood. It's on a full curtain wall system, but they wanted the curtain wall to be wood. So we designed a wood veneer curtain wall that was semi-unitized. And so if you start mixing unitized and site built together, there's some connections and things that could be better. And we did a PMU, and there were a lot of structural issues. The way the connections went together, the wood split. And the other thing too is the speed and candor that this went together, you can see a lot of mold on that wood, right? It got left exposed too long, and so some, real risk there to construction there, especially on this high-rise building that it would potentially getting wet. So we learned some things along the way, how not to connect wood together, and better ways to anchor into wood. And it's nicer to have larger pieces of wood you can connect into instead of curtain wall systems, or instead of veneer systems here. So still pushing this along, and there's still an opportunity here, but it's just how you do this. It's borrowing some of the ideas from aluminum, like embedded anchors like that. Better way. So continuing to tinker. And the idea is, curtain wood, or the concept is curtain wall connections, because we use them all the time in high-rise buildings with wood. And the idea with that is we know we can get, it's something that's mass-produced already. Anyone could do this. You just take your curtain wall parts, put it on the perimeter of wood, come up with some joinery. But the idea is to make this bigger than just something that one person can do in a proprietary nature. So the concept is out there as this. So the next catalyst, so to speak, for prefab mass timber facades is this project that started many years ago, and it's in an area of Vancouver that's very slow rezoning. So we had a lot of time to do some R&D, and so the idea and design for this building was a fair amount of mass timber on a building that could be probably 20 to 40 stories, depending on what the city finally allows. And it, highly glazed. It's got balconies on the outside. We'll get into later on as well. But essentially something that can we do this out of mass timber? So we're going to use this opportunity. We had some funding to do some testing and actually push this further. And so as part of the funding, we envisioned this competition. And the idea was the competition to get ahead of the need for this low carbon, low energy wood-based facade and test it out, prove it out, use that time to de-risk this, because that's what we wanted on this building. We approached over 40 companies, some of them in the room here across North America, of varying backgrounds. Facade contractors, window suppliers, anyone that could do something prefab or window side, mass timber side, new startups. And we ended up with 6 submissions. You got 1 partial and 5 complete and completely viable product entries, and narrowed it down to a top 3 here. And I'm going to talk a bit about those and what we learned there. So the top 3 were each contracted to produce a mock-up. So they actually get to physically, get some R&D money to do that. And the top team went through a performance mock-up, which we just recently wrapped up here, and I'll share some of those results. And through this, just helping the industry along to, can we do this? How do we do this? Let's learn those bad lessons before we actually do this at a large scale. So the key design parameters, wood is the structural element. We want this prefabricated as much as possible so we can do tall buildings. We want this architecturally flexible. We need large floor-to-ceiling windows. We need balconies, potentially. We're going to always have mixed systems like curtain walls and roofs and roof decks. Suitable for high rises, like that building, in a high seismic zone, and of course, meet all the fire code requirements. The other kicker in here too, it's got to be passive house ready, so that we actually set a high target of our 40, could have been our 30 or so, but essentially a high thermal performance, R6 windows for Vancouver anyways. Minimal thermal bridging, looking at all of the aspects there, so you couldn't have big anchors and things reducing your thermal performance, and airtight. So it's got to hit a high thermal performance. Cost, you got to come in competitive with other systems in the market, otherwise it's just not going to fly. Okay? Durable, of course, high water tightness, low embodied carbon, and then socially equitable manufacturing. Just threw everything in there, right? So the 6 entries, we had Element 5, Sidewalk, Katera, F3, Manic Isaac, and Tree Construction. We took all of their systems. We had a judging panel that I wasn't involved with, because I'm involved with a lot of the facade side. So they judged these all. They took all the submissions and looked at them. Neat systems. You got Manic Isaac had a wood curtain wall type system with just sort of panels. Tree Construction had some concepts. F3 Timber Technologies had a SIP with a big SIP panel that was connected together. And then we had Element 5, Katera, and Sidewalk, which used a mass timber panel with exterior insulation, rain screen cladding, and as part of their facade system for their overall building systems they were working on. And the top 3 systems out of the judging there were Katera, Sidewalk, and Element 5. And when you look at these systems, the Element 5 system, it's essentially using CLT. Now, there's a foot of insulation just for scale there. Most projects aren't going to need a foot of mineral wool insulation. Maybe half that. But we are seeing a lot of projects with like 6 to 8, 9 inches now of exterior insulation in our market for passive house. Rain screen, their connection details a steel to wood connector with some foam gaskets and an interlock there. Their vertical joint, a spline that could be connected on one side or both there, and using a lot of tapes. The Katera system, which was an evolution from the Catalyst project, interestingly, they took an approach for I'd say a purist approach, where they used wood as the structural connections. They used plywood as a spline and sort of working through that with some gaskets, with exterior insulation, rain screen. You can see the spline connection there. So interlocking spline with gaskets, way into the system. It's like, this is like 14 inches from where the water, is potentially getting into your system. So you're pulling it away. Corners there, some improvements from the catalyst job, something flexible there. Anchor systems. The anchor systems are all essentially buried at the slab edge, and that's important too for fire. Is if you have a fire, then the brackets need to be protected, right? So they don't fall off the building. And so all these systems, this would be under topping, and then at the exterior mineral wool and a fire stop. Given Katerra is no longer, this system is actually being sort of picked up by FP, and they're doing some R&D. And the idea with this system is, could you develop a system, we haven't gone through all the testing yet, could you design a system that anyone that wanted to do a prefab CLT panel, load bearing or not, could we give them a kit of parts, an Amazon gasket, to make it super simple, that anyone could do this and actually have it work? And so we're going through some R&D right now to try to push a fully generic system that would be open source that anyone in the industry could use. And this, we haven't got it far enough along yet, but the concept is essentially something like this, all wood. Sidewalk Labs submission there, mass timber, so they use a mass plywood panel instead of CLT, and they actually use the aluminum curtain wall joinery with some custom gaskets at the vertical to do a split gasket type configuration. The brackets hanging off the slab edge and be buried in mineral wool for fire protection. Full adjustability with something like that. You can go in and out, up and down to get the panels, lined up, and then the chicken head there. So when you look at these, there's a lot of similarities in the approach and the fabrication. They all used mass timber structure, 4 inches of CLT or LVL or mass plywood panel, dry joints. Right? We evolved from the sealant. You could actually use sealant joints in any of these or silicone strips, but they all evolved to something that's dry, different, and proving out those dry joints to keep your building wet or keep it from getting wet. Dry joints keep your building dry. All of them used an air and water just to barrier on the wood. They all used mineral wool for fire protection. They all had rain, a cladding support system, whether it be a clip or a long screw through the insulation. The great thing about a foot of insulation on the wood and with mass timber, you can screw in anywhere, right, through the cladding support to attach your cladding back to. And they all have a rain screen. So there's all a lot of similarities, and this is sort of the generic concept that, we sort of see as being the most viable going forward. Structure, warm and dry, protected by, air, water control, insulation, rain screen. And just the magic and the differentiation I think we'll see is how they come together, right? Proprietary or not, patented or not, you're going to have some way of connecting these together. And that's where the differentiation is, and hopefully we'll end up with some systems you can just buy off the shelf eventually. Now, the winning team went through a trial PMU and acoustic testing. So it was fun. We actually got to do some acoustic testing of mass timber walls between suites, between floors. The STC ratings are all there. Favorable results, good results. I'd say that, comparable to other systems, even between suites, we found that the joints between the panels actually helped a lot with the flanking transmission. So one of the things is if you span mass timber across a wall and use a butt, a demising wall, there's a lot of flanking. So if you put a joint in that, it actually helped a lot for acoustics. So this is the PMU assembly. This is the structure. So we got it moving in 2 directions here, and up and down. So it's 3, sort of all axis of movement. You see the base here. The gasket going into the aluminum component there, so as a starter, just like curtain wall. It's exactly like curtain wall. If you understand curtain wall, similar pieces, and even the trades and could be picking that up, right? The panels coming in. Little video here, you can see, flying. Now I would say that mass plywood panel could do with some aesthetic improvement on the inside if you're gonna leave that exposed. You could just veneer it, of course, but these are just sort of rough panels there. How do you get that last panel in? The last panel comes in and just sort of butts into the corner, and the connection there is slightly different. It's just on the inside instead of it's installed from the inside rather than as the panels come together. But this is all dry seals. Where they come together, they're sealant. You got structural silicone coming together, but you've got joints that allow this to slide around on itself and remain air and watertight for whatever you want to throw it at. So you can design to that aspect. The fun testing now, right? So the PMU testing, of course, you're doing dynamic and static water testing. I got a little video here in a second. The infrared, the thermal testing. So with thermal testing, it doesn't look like a lot. You do run around with an infrared camera though and see where there's cold spots. And some of the ways we connected the windows in could have been better. But are you getting transmission through that wood? No. And the joints here are buried behind several inches of insulation. So the thermal bridging here is all inboard of your insulation, and the insulation comes together tight, or you install a piece of soft insulation there inside. And so thermal bridging, pretty much continuous, and you're really dealing with your window perimeters. So again, you can sort of see the amount of water you're spraying at these things with this dynamic test there. Drones are great, aren't they? You just fly around and don't get wet. And then my favorite, and this is really fun, this is the inelastic. Now, would you like to have that in your building in an earthquake? It worked. There's a lot of benefit of a deep cavity. You can do a lot of stuff with cladding attachment and just where it's fixed and where it can slide. Look at it go. How many people have seen buildings move? There you go. Something new at summer camp, right? Oh, go the other way now. Look at that. So it all worked. It was successful. It didn't leak, and it didn't fall off. Right? Did we win? Won so far, right? Fire testing. Now, NFPA. There have not been any NFPA 285 tests until very recently on mass timber. This was the first. Trying to get this out in the industry, and we're trying to get this released so it can help the entire wood industry. But in the NFPA 285 test with 4 inches of mineral wool, the wood and the WRB didn't even know there was a fire. They got to 140 degrees or something like that, like on the WRB. They had Fahrenheit, right? And so it was hardly an issue. So NFPA 285 and mass timber, really not worried about it with mineral wool on the outside. Now, you could play around with different types of insulation to maybe a different result, but 4 inches of insulation, which we feel is probably the minimum you're going to see in a lot of these systems, was enough. So that was a good result, like I say, trying to get that out. Now in Canada, we have S134 testing, which is the alternate to NFPA 285. It's a bit harder test and different configuration. No way to test that in Canada. We have to go to labs in the US to do that. But there is a test baked into our code that already has CLT with 4 inches of mineral wool on the outside. So in Canada, the way we're getting around the fire testing is there already has been a test to demonstrate this can work. And so a lot of fire code consultants will use that. Now we've got this. And then we did a 2307 test. Weren't sure about this one. This is like 2 to 3, or we did a 3-hour first and we did a 2-hour. Both passed. So with the anchors protected by mineral wool on the bottom and the top, and a Hilti product for smoke seal, we were able to get a 3-hour floor-to-floor rating that passed this. And so this is for your first time doing something like this, you're kind of scared. Is it going to work? Because 2307 is not yet in all building code requirements, and it sort of varies, but newer codes are starting to adopt this. 2307, 3 hours of fire below, into a window. Of course, the window outside breaks and comes in. You don't want the glass to fall through your fire stopping and stuff like that. But with the mass timber floor, mass timber beam, and that bracket, and gypsum, obviously on the ceiling in this test, we're able to get to that. So if you need the 2 or 3 hour, how do you do this? It's encapsulation plus a bit of char that is allowing you to get to 3 hour. Yeah.
So when you say char, you're talking about somebody modifying?
No, sorry, it's char depth. Yeah, char depth. So, can be done. So, huge success in terms of getting it done. Now, there's some parallel work going on. How do you do balconies out of mass timber? And, you know, I don't love sticking mass timber out through the building and having the edges get wet. And so for this project, we said, okay, well, let's do bolt-on steel balconies, and we could put wood cassettes inside. And so we came up with a steel structure, and it's bolted through the facade system. It can either be bolted to the facade system or through it with knife plates. And we'll use stainless steel to keep our chi values, our thermal transmittances down as low as possible. Maybe we'll you can just thermal breaks as well. But essentially just knife plates to support these, and then you can either tension support, or this particular one was a compression supported bracket. Biggest concern with balconies is water, so they can actually see the wood in here, but then we got full waterproofing over top. And, you know, there's like that nice steel perimeter that prevents the water from going underneath, and drip edges. And John's talked about drip edges here in the past, but drip edges work, right? The biggest focus here was like, is this going to get wet? Is it going to be a problem? And you know what we found is that it will be quite dry if you have good details and waterproofing and keep the water from getting to that mass timber. So this is sort of the next iteration. So now we have a facade system and a balcony system that we have some confidence in for this particular project. And so the last one here, this is a company that we're working with that didn't enter that competition but has a system now, and they just wrapped up their PMU and had very similar successful results as we saw with the other one there. But essentially the same thing. This one looks a little nicer on the inside. It's mass timber, or CLT I should say. But the concept's the same. And this concept's there. It's not, you know, that difficult. It's not patented. It's a system that people can take and develop their own. So with that, you know, there is this market, there is this, we're getting ahead of it, still in that R&D phase. We're starting to see some of the first projects being built, and we'll learn from those, and we'll keep iterating. You know, the things we've learned over this, you know, mass timber buildings, especially taller ones, I'd say, you know, below 6 stories you could get away with stick building, but with the taller buildings we need, especially 12 and 18 stories like in our codes in Canada and the US, we need something prefabricated. It could be window wall, could be curtain wall, but we need those for speed and moisture and fire protection. You know, in Canada and the US, we can't go more than 4 stories unprotected for taller buildings, and that includes the facade. So you're not going to, you know, build 4 stories, stick build, you know, and then, you know, do that. You're going to try to go fast, and this allows you to do that. Systems need to be thermally efficient to meet our energy codes, and this typically means more wall than window, and that's why we're seeing a shift to a need for mega panels with punch windows rather than curtain wall that's entirely, you know, aluminum and glass and low thermal performance up into the state with spandrels. 3 systems have gone through this process and have all demonstrated the ability to meet the demanding needs of high rises and high spec. It can be done. The cost, I know I was going to get the question on cost. The cost is actually being comparable to cold form steel in our market, and a bit less than aluminum. But it's playing in the same realm as other facade systems. And the reason for that is the wood is actually relatively cheap, part of this. And a piece of CLT like that is a minor cost when you look at, let's call it like 5 to 10% of the cost, the material cost, or sorry, total cost of that material. We can get them to carbon neutral if we look at sequestration and to offset their materials, and coincidentally we can get them to 0 because we can offset the other stuff that we're using with that mass timber. So it's been a lot of fun. This has kept me, you know, quite busy during COVID, and lots of Zoom calls and, you know, factory visits and things like that. With that, we're done.
Questions? No.
Great presentation, Graham. I'm Christoph, Positive Energy. Joe, I feel like your mastermind on this is like expanding systems view out to the overlap of the health sciences and the building sciences, the grid and buildings, Kimberly and Brian coming up. So with that in mind, Graham, trees come from forests. And forest management practices, environmental changes have led to, like the Canadian forest industry for many decades, is a net carbon emitter. So to say that trees are then carbon sequestering is pretty suspicious. So I'm just curious if that awareness is present, and specifically Forest Stewardship Council wood, not SFI wood. Is this something people are asking about, talking about?
Yeah.
Is it happening? Thank you.
And that's why I presented both. Like those numbers, the CLT, these are EPD numbers, right? And so you can either with storage or without. And so, the number, the big number, where it's, it's doing pretty good, right? It's comparable to other systems. But there is the opportunity with proper forest practices, and the right harvesting, to get to those lower numbers. And that's the goal, right? And I think that when you look at this, you create this awareness that, hey, we need to do better or have better forestry practice. I think that's already there. And we're just going to see that number come down. It shouldn't go up. But we get a lot of questions about, is this, trees and carbon storage, how do you get that true number? It'll help. So all like everything we've learned in the last couple of days, it's lots of things we need to do to come together, and they are coming together on some projects, which is kind of cool.
Karol Kazmierczak, Building Enclosure Institute. I wrote full 2 pages while you were speaking, so you wouldn't be...
One question.
One question. So... Understood. So what I was missing here was the comparison, good, bad, and why between the wood panels that you presented and the rest of the more, say, traditional quote-unquote systems. And some areas that I particularly found lacking, with all due respect, were longevity at the beginning of your presentation. Then obviously the issues of stiffness of wooden assemblies. For example, you showed us smoke pathing through the windows without telling us what the hardware was, right? The obvious benefit of wooden assemblies is that they are much stiffer than other, and then that benefit conveys into, if you have a perimeter hardware, you don't see any. Then it also conveys into another great benefit that I found lacking, and I hope that you can expand the noise resistance. So we probably want to take that conversation, into Joe's backyard.
That's the question.
I'd say the comparison. Yeah. So I think with these panels and using mass timber, they're all in the warm and dry, and they're exposed to the indoor humidity, right? So you got to factor that in. But they're not getting wet, right? And they're not in a high humidity environment in that location. You're protecting them with good building science of exterior insulated assemblies, right? But they are stiff. That's why you notice the connections are flexible. And when as a facade system, this behaves more like precast than it does curtain wall, even though you're using curtain wall parts, because they are stiff. And so they actually drift rather than rack or translate. And so that was part of doing the PMUs, is we learned that these all really drift. Now you could make them flexible. You could add flexibility in so that they actually rack. You could add studs, say, in between. But there's, or you could design the connections in such a way that you could rack. It's just that becomes a bit of a, as you know, you do a lot of this, facade engineering challenge. So, but then compared to their systems, I have confidence that it can be structurally just as adequate as steel or aluminum in the same considerations that you're building in. So keep it dry.
Graham, thanks for your presentation and for being an ambassador, really, of mass timber. That's great. I work at the Canadian Wood Council. My name is Rob Jonkman. I just wanted to just modify something Joe said yesterday and elaborate on what you said today. You said in your rush to get to the beer, you said wood burns, but you forgot the last part that Graham talked about, which is wood burns for a while until it doesn't because of the charring effects, and you brought that up really well. And just in anticipation of some questions I've heard, but what happens if it burns and chars? The beauty about the mass timber is it can actually be removed, scraped off. The char can be scraped off, sanded, and a new sacrificial layer bonded to that. So that's one of the beauties of wood. And the second thing about charring is in Canada, just 2 months ago, we did a mass timber demonstration project that showed a very large CLT building burning. We had all kinds of people watching, firefighters and everything, and it was a thing of beauty because it was burnt with the proper amount of fire, and then it burned for only 30 minutes and slowly by itself went out because of that charring effect. So it really does work. Thank you.
Just got to design,
question in there, right?
Design to your materials, right? I mean, yeah.
No, I'm just messing with you.
Oh, sorry. Lou got missed up front.
No.
I'm hanging around, so I'm not going anywhere.
No, I'm going blind.
Yeah, not a question, just a comment that there's a lot of smart people here. And I just want to make sure that we support each other, not only professionally, but also support each other's mental health and through the good times and also when life gets tough.
I didn't see you.
Yeah, conveniently sized for small spaces, Joe. Yeah, Graham, I'm fascinating stuff. It's great, and I'm wondering about longevity and about monitoring long term. You know, when you think about what you've seen there, and obviously every system is going to be different, but you probably want to know about moisture content long term. So I'm sure you've thought about it. Specific locations, and what are the numbers in terms of wood moisture content? That those two things, locations and moisture content percentage, that would begin to be an appropriate concern to take action.
Yeah. So the systems are all, essentially waterproofed on the outside. They're in a factory. They're all, basically 5 sides are covered with something to keep. And the edge grain is really the most critical, but in a lot of those cases, they're covered by, aluminum or something else, right? Membrane. So the biggest risk to these is actually during construction phase, and water getting to the backside or running down the backside. And generally it's hard for water to actually go through mass timber through that phase, right? And so, and usually these have some sort of water repellent stain on them. And so I would say during construction we manage it that way. But in service, that wood is inboard of all of your insulation. I mean, there's a bit of insulating value itself, but it's following the humidity of the indoors. And it's really tracking, it'll come to equilibrium over years with the indoor conditions, unless you have a leak, of course, and then you look at the joint details and so forth. The leak, or if the water leaks in those systems, does it actually touch the wood? And that's one of the things that we've taken away that risk with these systems, right? At the same time, if you've got, a foot of insulation on the outside, and we've done testing and other people have as well, it's hard to get a lot of water back through that much insulation unless you're dumping it in and have bad details. So a lot of this goes...
Unless you're air conditioning.
Yes. And so, yes, I would love to approach this in a hot, humid climate, and that's where you definitely would have some water in there and then condensing down. So.
Graham, great presentation, a lot of information, so thank you for that. Keith Nelson with ECS, a comment and a question, if I may. Safety minute for the contractors in the room. You went in the chamber during nitrogen-cooled thermal cycling. That's scary. Don't answer. I hope there's a confined space protocol in place with air monitors.
Yes.
That being said, so one of the pieces of feedback I've gotten talking about mass timber is the increased tolerance in the construction. And that instead of dealing in quarter-inch, half-inch, inches of materials being out of tolerance, the mass timber, they're talking 1/16 of an inch. And the time and effort savings in having to correct those issues. I'm wondering, with your experience, have you seen that in the facade, and are there benefits that you can pull out of that for the system?
I would say that, so the structural engineers have told us that you could design these for like quarter-inch, 1/8. We don't believe them yet, so our facade systems will design for an inch, or like we're not going to, go down from where we're used to for a facade system. So you could, there is this, there is tighter tolerance, but there could be with any precast and even steel. Like you can get to those better tolerance. Concrete's a bit harder. Wood and anything prefab is a little easier. But do you want to design for a smaller tolerance now? Do you need to? I mean, you look at you're all hiding all that stuff that's in there. So no, we're not buying the 1/4 inch movement yet.
Hey, what are your thoughts on integrating mechanicals into the facade, including thermal distribution? So what we're starting to see, I talked a little bit about overclads.
Yep.
So you're seeing panelization around overclads. There's companies like Dextol and Stowe that they're starting to think about that.
Yep.
A lot of them are starting to think about integrating pipe and other mechanicals, energy recovery, ventilation, that sort of thing into the panel. What are your thoughts on that?
You could easily put stuff in there if you wanted to, electrical and other services. It's the connections, right? So you need a flexible connection with the tolerance and everything else that plugs together or connects together. It's the same with modular, right? Like modular, you do the whole suite and then you run it out to the corridors and you just run everything in the corridor. You could plug parts into these systems. You could hide them in the exterior insulation, but then you got to look at maintenance, right? So it's like if you put something outside of that structure, you got to go to the outside to fix it, right? So you might tend to put it on the inside, or just don't put in exterior walls. But I know in the retrofit case, yeah, there's desire to run ventilation through the facade, and yes, you could.
All right, the last question, and it better be a good one.
No pressure.
So I'm only allowed to ask one, so I'll give you a choice of 3, and then you can decide which one you want to answer. The 3 challenges that I've been experiencing on mass timber projects in our practice has been unreliable LCA data, or non-accessible LCA data, especially in regards to transportation carbon. The other one is not a robust amount of historic cost data for estimators to reliably give our clients financial information on the decision of whether or not to embark on that. And then finally, the other challenge is with hybrid systems, especially steel CLT hybrid systems, and the mixing of structural trades and the complication that brings. So I guess I'm wondering if you can either direct to some resources or if you can potentially talk to that cross-trade relationship.
Well, I mean, costing, that's, everything's bananas these days, but, looking at, you can get, if you have experience doing that, you can get cost data, but the LCA one, I'll tackle there, and putting together this data here with this crowd, digging deep again, practicing digging deep, and even then, there's still some uncertainty in that, right? And those are what it is, August, whatever day, 4th, 2022. Those will change, and I think with EPDs and any material and embodied carbon, we need to stay on top of that. And I think it's practices. You need someone that's a leader in that's going to keep the up-to-date information. Look at the styrofoam industry. They've made a huge impact, yet people still talk about old data, right? And so, and the wood industry, we're slowly going to get better. And so, the key thing is keep on top of the latest and don't regurgitate the old misinformation. So.
All right. Thank you. Woo-hoo. All right, lunch break. Everybody back at 1 o'clock for a fabulous pair of closing presentations.